All right, folks, what we're going to do in this video is we're now going to talk about two-sample hypothesis testing. So what we've done over the last few days has been one-sample hypothesis tests, and now we're going to go into two-sample hypothesis tests. Now, here's the idea in a two-sample hypothesis test. I got to compare it to the one-sample hypothesis test so that you can understand how they're different. In a one-sample hypothesis test, you were comparing a population to an unmoving number, okay? So you just had a number which was the population mean of some group, okay? In fact, we could even say that it's not even mu. It's just some number like, like 87. And all you were trying to determine is whether the population you were sampling had this as its mean. And so sometimes the probability distribution might be over here, and here was the population mean. And you would say, wow, well, or excuse me, not the population mean, the sample mean. And here's the sample mean. And what you're trying to say is, well, what is the likelihood that this sample came from a population that has a mean of 87? Well, with how far away this distribution curve is from this sample, it's really unlikely that that sample, or it's less likely that this sample came from this population. But let's say that you took a sample, let's say that you took a sample and its distribution curve looked like this, right? Where this is the sample mean x bar. And you can see how this distribution curve is a lot closer to 87. And so it's more plausible to believe that that sample came from a population that has a mean of 87. And that's basically what we've been doing. And then there are other situations where maybe your mean from the sample could have been all the way over here, x bar, but the distribution curve looked like this. The variance was so wide on the curve that it was still plausible that that sample came from a population that has a mean of 87. And so in a one-sample hypothesis test, you are testing a sample to an unmoving number, to just one objective value, and you're wondering whether that is the mean of the population that the sample is taken from. But now what we're going to do in a two-sample hypothesis test is there is no number. There is no unmoving number. The number, or instead what we're going to do is we are going to compare two samples, and each sample has its own distribution curve. And let's say you have one situation where this is a sample. You have a sample that has a sample mean and it has a standard deviation. It has its own distribution curve. And you know how to make a distribution curve out of sample information. You did that weeks ago. Okay? So this is basically, you'd have a number here, the sample mean, and you'd have standard deviations. You'd have your hash marks over. But now what we're doing is we're taking another sample. And let's say the other sample has a mean right here. And that sample, its distribution curve looks like this. And the question we're going to ask is, what is the likelihood that these two samples have the same mean? What is the likelihood that both of these samples have the same mean? Okay? And we can do that by taking two samples and comparing their values, comparing their the mean with the standard deviation and the sample size. Okay, we can calculate a z-statistic that will determine whether these two different samples have the same mean. Could they come from populations that have means that are equal to each other? And then in many cases, the idea is we're trying to determine whether the two populations are basically very similar populations, or are the two populations very different populations. So this is one possibility, and I might argue, given these two curves, that they came from similar populations because there's a lot of overlap, right? You can see a lot, both of the curves are overlapping each other. On the other hand, what if we had this situation? What if we had a situation where one of the curves, or one of the samples, has a distribution curve that looks like this, and the other sample has a distribution curve that looks like this? With the mean. And there's not very much overlap. You can see that this distribution curve is very distinctly separated from this distribution curve over here. And in this situation, we might conclude they don't really overlap. They're so tight in their variance that it doesn't look like they would come from populations that have the same mean. Okay? And so the way we do this, we don't necessarily have to draw the curves per se, but what we can do is we can do a hypothesis test that's very similar to what you have already done. So what I'm going to do is I'm going to go ahead and put all the steps that you already know up on the board. All right, so here are the 6 steps that we have been using to do a hypothesis test. We've used these 6 steps for a 1-sample hypothesis test. We're going to use the same 6 steps for a 2-sample hypothesis test. But there are going to be differences in 2 of the steps. The first step and the last step are going to be slightly different than what you're accustomed to. Okay? Now, what I'm going to do right now is I'm going to show you how the calculation for the test statistic is different, and then in a few minutes we'll focus on how the null and alternative hypotheses are different. Okay? But in order to explain to you how the calculation, the formula, you use a formula, right, for calculating the test statistic. If it's a z-test or a t-test, you've been doing x bar minus mu divided by s standard deviation over the square root of n. And what I'm going to do is I'm going to modify this calculation, this formula, so that you can calculate a z-statistic for a 2-sample hypothesis test. Now, in order for me to modify this formula, I need to talk a little bit about this denominator here. This s over the square root of n. I want to show you something. Before I talk about that, I want to show you an example of a simplification with radicals, with square roots. Let's say that I had the square root of 5 over 7. Now, I don't know if you know this, but this is the same thing as the square root of 5 over the square root of 7. So you can actually split up. If you have a square root of a fraction, you can actually split that square root into the numerator and the denominator. Okay? So that's the first thing I want to show you. Now I want to show you, what if I had the square root of 9 over 7? And then that would be the square root of 9 over the square root of 7, right? But the square root of 9 is actually equal to 3. So this would be equal to 3 over the square root of 7. And this is what you would have, as the standard error if your standard deviation was 3 and your sample size n was 7. This would be the standard error. But now what I want to show you is we can go backwards. We can take this and go backwards to this. Let me show you what I mean by that. What if I started with 4 over the square root of 5? If if I started with 4 over the square root of 5, I could turn this whole thing into a radical by first squaring the numerator and putting a radical on it. So if I square it and then put a radical on it, it's still the same number. So 4 squared is 16, and then I'll put a radical on it, a square root, over the square root of 5. And so this is the same thing as 4 over the square root of 5, which is what we had started with. So 4 over the square root of 5 is the same thing as the square root of 16 over the square root of 5. And we're going to go one step further. We could turn this into a single radical, the square root of 16 over 5. Okay? Now, if you can understand that, you may have to go back and watch these steps just a few times to make sure you got it. Or you can skip ahead to the formula. I just want you to understand why the formula is changing the way that it's changing. The idea here is this, is to go from something like this to something like that, you have to square the numerator and then put a square root over it and then simplify the square root into a single square root. So what I'm going to do is I'm actually going to take this s over the square root of n, and watch what I'm going to do. I'm going to square the numerator and put a radical over it. So I'm going to square it and put a radical over it. All right, so this is going to become s squared, and it's the square root of s squared, over the square root of n. And this is the same thing as this. And what I want to show you is, do you remember what s squared is? Go back to the first few days of our class, and you might remember that s is standard deviation, but s squared is the variance, the sample variance. Okay? So what we have here is the square root of the variance over the square root of the sample size. But I could make this a single radical, and I can make it a big square root of s squared over n. And so this is the same thing as the square root of s squared over n. Okay? And that's important to understand because we're about to now go into our new formula for the z-score. Okay? So the z-score for a 2-sample hypothesis test goes like this. Z is equal to, instead of having x bar minus mu, see, we have 2 samples. That means we have 2 sample means. If we have a population A, like here in this problem, if we have population A and population B, each one of those populations, if we take a sample from population A and a sample from population B, each one of those samples is going to have a different sample mean. And so we're not going to have a sample mean compared to an objective value. We're going to have a sample mean compared to another sample mean. So we're going to have x bar minus x bar. We're comparing the 2 means of the 2 samples from the 2 populations. But we want to make sure that we clarify that this one is from population A and this one is from population B. So the numerator of our formula is going to be sample mean of from one population minus the sample mean from the other population. Then all over. Now, what we have to do for the standard error, instead of having the standard error of 1 sample, we're going to have the standard error of 2 samples, 1 from each population. And so this is what that's going to look like. It's going to look a lot like this. It's going to be the square root of s squared over n. But there's 2 s squareds. There's 2 standard deviations. One of them is from population A, and the sample size is also from population A. Now we need to incorporate the variance from population B, or the standard deviation and the sample size from population B. And the way we're going to do that is we're going to put plus s squared from population B over the sample size from population B. And this is your formula for calculating the z-statistic. And I know it looks really nasty, but that's the formula. And so what you're going to have to do is you're going to have to be extra careful when you're plugging all your numbers in to make sure that you get the correct z-statistic. Okay? Okay, so I've gone ahead and I've put the formula for our z-statistic down here under step 6, and that's what we're going to use when we're doing our hypothesis test. So let's go ahead now and let's work through this example. Let's do a 2-sample hypothesis test. This says conduct a 2-sample hypothesis test at the 0.05 significance level to determine whether the mean of population A is different than the mean of population B. And then it says we got a sample of 45, that's n sub A, the sample of 45 from population A that resulted in a mean of 121 with a standard deviation of 13.5. So this is S sub A and this is X bar sub A. While the sample of 67 from population B, so this is the sample size from population B, this is N sub B, resulted in a mean of 113. This is X bar sub B with a standard deviation of 15.7. And then this is the standard deviation of population of the sample from population B. This is S sub B. Okay? So here's the deal. It says do a hypothesis test to determine whether the mean of population A is different than. It doesn't say larger than. It doesn't say smaller than. It says different than, or different than. And if you think of our 3 different kinds of null and alternative hypotheses, remember, when we do the alternative hypothesis, let's put H sub O and then H sub A, that we sometimes, so we got mu, we can either put not equal to here, or we can put greater than here, or we can put less than here. And remember, what you put here is determined by what kind of test you're doing. Well, different than doesn't say more than or less than. In fact, different than doesn't care whether you're higher or lower, just that you're not equal to. And so that's why this test, this particular 2-sample hypothesis test, is going to be a not equal to test. Okay? But here's the thing is, in our 1-sample hypothesis test, we were comparing a population mean to a number, to a constant value. But in this one, we're comparing a population mean to another population mean. And so we got to put another mu over here. So its population mean is not equal to another population mean. But this is the population mean from population A, and this is the population mean from population B. And so what we're hypothesizing here, what we suspect the test we're performing is saying, do a test to see if the mean of population A is different from the mean of population B. And that would be the alternative hypothesis. But the null hypothesis would say, well, we're just going to assume that the means of the 2 populations are equal unless there's statistical evidence to suggest otherwise. Okay? So we've got our null and our alternative hypothesis. Now, because we're doing a not equal to, is this a left, a right, or a two-tail test? Well, remember, not equal to indicates a two-tail test, right? And now what is our alpha going to be? What's our level of significance? Well, the question tells us that, tells us our level of significance is 0.05. So our alpha is 0.05, and now we need a p-value. And because this is a two-tail test, we have to split the alpha into 2 tails, evenly into 2 tails. So we're going to divide the alpha by 2, which would give us, so 0.05 divided by 2 is 0.025. So our p-value is 0.025. And now, is this a z-test or a t-test? Well, the way you determine that is based on whether the sample size n is less than 30 or greater than 30, right? Or less than or equal to 30 or greater than 30. And here's what I'm going to tell you. Since there's two samples, if either one of the samples is 30 or less, it's going to be a t-test. But if both of the samples are larger than 30, then you can do a z-test. And we're only going to do z-tests today. But look, we have a sample size of 45 and another sample size of 67. They're both higher than 30, so this is a z-test. So we're going to do a z-test. Okay, that's step 4. Step 5, identify the critical value. So in order to identify the critical value, we're going to need a z-table. I have a couple z-tables right over here. All right, so hopefully you have a z-table also. And so in order to identify the critical z-value, which we'll call z-crit, we have to look up the p-value, 0.025. We've got to look that up in our z-table. So if I look up 0.025, here it is over here, I get negative 1.96. Negative 1.96. But now let me remind you that this is a two-tailed test. So we're doing 1.96 on both sides of the curve. So we need positive 1.96 and negative 1.96. So as all two-tailed tests are always plus or minus. So we got plus or minus 1.96 is our critical z-value. And then if we wanted to draw a distribution curve here, we could put the right tail and the left tail, and over here we would say negative 1.96, and over here we would say 1.96. Okay? And then our decision rule is reject H sub O if, well, there's two possibilities. If our z statistic is less than negative 1.96, or if our z statistic is larger than positive 1.96, we will reject H sub O, just like we've always done. This is no different at this point than any of the one-sample hypothesis tests. Now we're about to see a really big difference, because now we have to calculate our z statistic, which is going to be a little crazy because we have a lot of letters in here that we have to fill in numbers for. Okay? So let's do this over here. To calculate the z statistic, we need to put in a bunch of numbers. We need to put the mean of the sample from population A, which is 121. So that's 121 minus. Then we have to do the mean of the sample from population B, which is 113. Put that right here. Divided by, all right, so now this is going to get sort of crazy. We're going to do the square root of, we got to do a square root in the denominator. And it's the square root of, now we got to do two, oops, I messed up my formula here. This is a plus. Sorry about that. It's a plus. Whew, glad I caught that. So what we're going to do here is we got two fractions in the denominator, and they're being added together. Two fractions being added. In the first fraction, we have the standard deviation of the sample from population A, which is 13.5. I'm going to put that right here, 13.5. And we have to square it, because this is S squared. So we have to put a square on this. And then in the denominator, the formula says we need the sample size, n, from the sample from population A. And that is the sample of 45 from population A. So this is our n, 45. Put that down here. Plus, now we're going to do the same thing, only with population B. We need the standard deviation squared. Standard deviation from population B, 15.7. So we're going to put a 15.7, and we're going to square it over the sample size from that sample from population B, which is 67. So put a 67. Now, this is going to be kind of crazy to put in your calculator, so be extra careful. This is what I'm going to do. I am actually going to put parentheses around the numerator. Now you could do this separately. You could do this separately and then this separately and then do it again. But I'm going to try and put the whole thing in my calculator. I'm going to put parentheses around the numerator. Then when I do the square root, I'm going to put parentheses around this, and then parentheses around this and this. And that should be able to give me a correct calculation. So I have a scientific calculator right here. And so I'm going to key in parenthesis 121 minus 113 divided by, and I close parentheses, so it's parenthesis 121 minus 113 close parenthesis divided by the square root of, so I'm going to hit second square root of, then I'm going to, now in my calculator, when I press the square root button, it opens up a parenthesis, but that parenthesis belongs to the radical. I'm now going to open up another parenthesis that belongs to this fraction right here. You know what, and technically I don't need to. You know what, I'm going to take them out. I'm going to show you how you can actually do this with fewer parentheses. Let's get rid of these. Because your calculator is actually going to do the division before it does the addition, so you're kind of lucky here. All right, so I hit the radical button, and so now all I'm going to do is I'm going to key in 13.5 squared, 13.5, and then I can either do to the power of 2 or just hit the square button, divided by 45. Then plus, then 15.7 squared, divided by 67. And then I'm going to close the parenthesis on the radical, and when I press enter, I get 2.878. And that's rounded to the third digit after the decimal. 2.878. Now hopefully you're doing this with me. Hopefully you're calculating this with me and not just watching me do this. You know, you're only really going to learn it if you write it out and do it with me. So this is our z-score, positive 2.878. And because this number is larger than 1.96, we're going to make a decision, and the decision is we are going to reject H sub O. All right, let's try this example, two-sample hypothesis test. It says conduct a two-sample hypothesis test at the 0.02 significance level to determine whether the mean of population A is less than the mean of population B. The sample of 81 from population A resulted in a mean of 50 with a standard deviation of 7.2, while the sample of 72 from population B resulted in a mean of 52 with a standard deviation of 5.7. Okay? All right, so we're going to do the state the null and alternative hypotheses. So we're going to do H sub O and H sub A. Okay? And let's see here. Determine whether the mean of population A is less than the mean of the population B. So mean from A is less than mean from B. So we're going to say the population mean of A is less than the mean of population B. And if that's the alternative hypothesis, then the null hypothesis is the mean of A is greater than or equal to the mean of B. Okay? So that's our null and alternative hypothesis. Is this a left tail, a right tail, or a two-tail test? Well, the alternative hypothesis is less than, so this is a left tail test. Left tail. Part 3, or step 3, our significance level, our alpha, is given at 0.02, and our p-value for a left tail test is equal to the alpha. So our p-value is 0.02. Is this a z-test or a t-test? Well, the sample sizes are 81 for population A and 72 for population B. They're both larger than 30, so this is a z-test. Now we got to identify the critical value. So what is our critical z value, our z crit? Well, we're going to get that from a z table, and we're going to look up a p-value of 0.02 or 0.0200. Okay? So if we look over here, we have 0.0262, 0.0233, 0.0288. Here we go. Oh, here we go. How about 0.0202? Then we have 0.0197. Well, which one of those is closer? 0.0202 is closer. So the z-score associated with that is negative 2.05. So z-crit is negative 2.05. That is our critical z-value. And now we can draw or sketch a distribution curve. It's a left tail test, so we're going to shade in the left tail, right? And our critical value for cutoff is negative 2.05. And our decision is that if our z statistic down here, if it's less than, if it's over here, less than negative 2.05, so reject H sub O if z is less than negative 2.05. That's our decision rule. All right? Last step, step 6, we're going to calculate z. Let's go over here. Well, let's write it in right here. So z is going to be equal to the mean of A minus the mean of B. Well, the mean of A is 50, and the mean of B is 52. Okay? So 50 minus 52 divided by, let's make this a little darker, divided by the square root of, standard deviation of A squared divided by sample size of A. Standard deviation of A is 7.2. We're going to square that, and we're going to divide it by a sample size of 81. So 7.2 squared divided by 81. Plus another fraction, standard deviation of B squared over the sample size from B. Standard deviation of B is 5.7 squared. So 5.7 squared over the sample size of B, which is 72. 72. Now I can plug all this into a scientific calculator. I'm going to put parentheses around the numerator, but the rest of this shouldn't need parentheses at all. Let's see here. Grab my calculator. Here it is. All right. I got parenthesis 50 minus 52, close parenthesis, divided by the square root of 7.2 squared divided by 81 plus 5.7 squared divided by 72. And I'll close off there's a parenthesis that got opened with the radical. And now when I just press enter, I get negative 1.915 equals negative 1.915. This number is not smaller than negative 2.05. Therefore, our decision is do not reject H sub O. So now, you might think that that means, oh, well then that means that the mean of population A is not less than the mean of population B. Well, actually, no, that's not what it means. Or you might argue, oh, well, that means the mean of population A is greater than population B or equal to population B. Well, no, not necessarily. All it means is that this study did not show support for the alternative hypothesis, so we fail to reject the null hypothesis. Failing to reject a null hypothesis does not mean that the null hypothesis is true. It just means that we didn't find enough evidence to reject the null hypothesis. Okay? And so that takes, it's just your mind, you know, it's hard to get a mind of research is to understand that we don't ever really fully prove the things that we're studying, we just show repeated support for them. And so we did not, in this case, show any evidence that we should reject the null hypothesis. And so we are going to make decisions and act in assumption that there's not really any difference between the population means, but it does not conclude the absolute proof that the mean of A is equal to the mean of B, okay? And it's just a finer point of research. It's a finer point of science. You really have to be immersed into the world before you really start to understand this mentality of you don't really ever fully prove things. We prove things in math. We have proofs in math. But in science, we show evidentiary support. That's what we do, okay? Okay, let's do one more example. All right, here's our third example of a two-sample hypothesis test. Hopefully you're starting to get the hang of this. Let's read this. It says, conduct a two-sample hypothesis test at the 0.01 significance level to determine whether the mean of population A is more than the mean of population B. Okay, so we can actually get our null and alternative hypothesis from that. Alternative or null hypothesis, alternative hypothesis. It's saying we're conducting a hypothesis test to determine whether the mean of A is greater than the mean of B. So that means the mean of population A is greater than the mean of population B. And therefore, the null hypothesis is that the mean of population A is less than or equal to the mean of population B. So we've got our null and alternative hypotheses. Okay? Is this a left tail, a right tail, or a two-tail test? Well, this is a greater than alternative hypothesis, and greater than means a right tail test. And now identify our alpha and our p-value. Our level of significance is 0.01, so 0.01, and our p-value. Now, I want to remind you that when we're doing a right tail test, that determining the p-value depends on whether it's a t statistic test or a z statistic test. So we have to jump ahead now to step 4. Is this a z or a t test? Well, we've got a sample of 45 and we've got a sample of 39. Both of them are more than 30. Therefore, this is a z test. And I want to remind you that in a z test, that to get the p-value, you have to do 1 minus alpha. So we're going to do 1 minus 0.01, which gives us 0.99. So our p-value is 0.99. We've already done step 4 here, so now step 5, we want our critical z-value. So z-crit, where do we get that from? We get it from a z-table. So I'm going to go ahead and get a z-table here, and I'm looking up 0.99. So if I go in the table and go to 0.99, I have 0.998 and 0.9901. Well, 0.9901 is closer to 0.99. So that's going to be 2.33. So my critical z-value is positive 2.33. You know, if you accidentally just used a p-value of 0.01 and looked it up in the z-table, you would get negative 2.33. And so knowing it's a right tail test, you could just then make that a positive 2.33. So you can overcome that error by just making sure your critical z-value is positive when you're doing a right tail test. All right, so let's sketch the curve here. So if we were to sketch the curve, it's a right tail test. So we're going to shade in the right tail here. And our cutoff score for the rejection region is positive 2.33. And now we can state our decision rule, which is reject H sub O if Z is greater than 2.33. There's our rejection rule, okay? Or our decision rule, sorry. All right, last thing we got to do is we got to calculate the Z statistic. So we're going to use our massive formula here. We're going to be extra careful putting our numbers in. We got like 6 numbers we got to put in. Got to put a number here, 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 and a number here. That's 6 different numbers. Then we got to be careful when we key it in the calculator. Be extra careful. Take extra time if you have to, but you got to get good at this. All right. So the mean of population, or the mean of the sample from population A is 16.9. So I'm going to put a 16.9 here, minus the mean of the sample from population B, which is 14.8. So I'm going to put a 14.8 here, over a radical, the square root of 2 fractions that are added together. So 2 fractions that are being added together. The first fraction is the standard deviation of the sample from population A, standard deviation of A squared. Population A, mean standard deviation of 2.1. So we're going to put 2.1 squared over the sample size of A. So N, sample size is 45, the sample of 45 from population A. So over 45. Now, last part over here, 2 more numbers. S squared, that's a standard deviation from population B. Population B resulted in a mean of, with a standard deviation of 1.7. So I'm going to put a 1.7 here, and I'm going to square it. It's 1.7 squared, because the formula says squared, over the sample size from population B. Sample size, population B, sample of 39. There's our sample size. So over 39. And now we're going to plug this into a calculator and see what our Z statistic is. I'm going to put parentheses around the numerator because that's going to help me to try and get, or to make sure that I do the order of operations correctly. So I'm going to go parenthesis 16.9 minus 14.8. Then I'm going to close the parenthesis, divided by square root of. So I'm going to do a radical here. 2.1 squared divided by 45 plus 1.7 squared divided by 39. Then I'm going to close the parenthesis on the radical. Just got to press equals now. I'm going to press enter, and I get 5.062. 5.062. 5.062, which is greater than 2.33. Therefore, our decision is reject H sub O, reject the null hypothesis. Now, does that automatically mean that the mean of population A is greater than the mean of population B? Not necessarily. However, this does show evidentiary support for that hypothesis. We may now want to go out and do a few more studies and find out if, with different circumstances, maybe an experiment, maybe a field experiment, who knows, different kinds of studies looking at the same question, we might be able to, if we get repeated evidentiary support, then we can be more confident in our claim that the mean of population A is greater than the mean of population B. Okay?